Hello and welcome back in the fourth video of the series about multivariate calculus. Today we're going to analyze line integrals. First, we look at what is a parametric equation. So a curve C can be defined with the parametric equation, for example, x, y, and z, and a parameter t that can vary in an interval between a and b. This can be summarized in the vector equation. So we call r of t the vector function, which has x of t, y of t, and z of t as the free components. We can see this function r in this way, a function that takes values of t in the interval ab and maps them to a point, a 3D point in this case, in the curve. Now we want to compute or understand what can be the length of this curve. We can call S of t the length of this curve between r of a, so like r in the first point of the domain of t, and r of t. Then we know that the change in S is given by the magnitude of the derivative of r. And this, as we know, the magnitude is given by this expression. In here, we have dx over dt since we have r prime. If we only had r, for example, we wouldn't have had dt. We can see this in the drawing as this ds, we can see it as the hypotenuse of this, let's say actually diagonal of the parallelepiped with sides dx, dy, and dz. And of course, this diagonal is given by this formula over dt, of course. We know that now, if f is a function of three variables that is continuous on some region containing C, we can define the line integral of the function along the curve as, this is the notation for the line integral, and this is equal to the function evaluated at x of t, y of t, and z of t times the length of the curve, which is given by the formula that we saw before, dt. In a more compact notation, we have, of course, the integral from a to b of f evaluated at r of t, while r of t being the parameterization, and multiplied by the magnitude of r prime that we saw before is equal to this formula. We see now an example of an application of this formula. In this case, our function f of x, y, z, is given by x plus y plus z. And the curve C consists of the line segment from the point 2, 0, 0 to the point 3, 4, 5. So from this point to this point. Then we have another point, another segment, so the segment from 3, 4, 5 to the segment 3, 4, 0. Now our plan of attack is first finding the parameterizations. We can use the fact that the line integral on C is equal to the line integral on C1 plus the line integral on C2. So, in this case, we want to find the parameterization first R1. So for C1, we have R1 equal to, for example, I take this kind of parameterization, but this is not unique. So we take 1 minus t that multiplies 2, 0, 0, plus t that multiplies 3, 4, 5. In this case, as a quick check, we see this parameterization is correct, because it's a segment that will give, is a parameterization will give a linear linear curve, and also it is that such that if we have t equal to 0, we have that we are in the point 2, 0, 0. While if we have t is equal to 1, we are at the point 3, 4, 5. So this means that it's a correct line since it passes through the 2 points that we want. So we can do the same for the second parameterization. It's a quick and fast way to find the parameterization of a segment by using this kind of structure. So 1 minus t multiplying the first point plus t multiplying the second point. In this case, we get 3, 4, 5 minus 5t. Now, all we have to do is apply the formula that we saw before. We can do it in this way. So we remember the function was this one. And we have a drawing here to remember what we are doing. So we first apply the formula for C1 and then we will do it for C2. So first we recall that we computed R1 to be this, and we can find the derivative of this parameterization by simply taking the derivative of each component. So we get 1, 4 and 5. We now take the magnitude of this. Taking the magnitude, we have here square root of 1 squared plus 4 squared plus 5 squared, and this is equal to square root of 42. Now, as we need this term here, we can simply evaluate the function f at the parameterization. So first term x, we have to take 2 plus t, so we have here. Then for y we take 4t, and for z we take 5t. And this will be equal to 2 plus 10t. Okay, now we can finally apply the formula, and we have okay, the line integral on C1 is equal to this is the function evaluated at the parameterization, and this is the magnitude of r prime dt. We simply compute this integral and we obtain 2 square root of 42t plus 5 square root of 42t squared from 0 to 1. And this, substituting 0 and 1, gives us 7 square root of 42. We repeat the same process for the second parameterization. So we recall that the second parameterization was given by 3, 4, 5 minus 5t. Then we can simply find the derivative of this vector as before. Now the magnitude of this vector gives us 5. And if we evaluate the function at R2, we get, so as before, for x we have 3, for y we have 4, and then for z we have 5 minus 5t. This gives us 12 minus 5t. So then we can substitute the things we found in the formula. That gives us the integral from 0 to 1 of 12 minus 5t that multiplies t. I forgot to mention, I take the bounds 0 and 1, both in this one and the other one, because so when t is 0, we have the first point, and when t is 1, we have the second point for both C1 and C2. And so in this way, yeah, 0 corresponds to A and 1 corresponds to B. So then we simply evaluate this integral, and we get 60t minus 25 over 2t squared. That gives, from 0 to 1, that gives 60 minus 25 over 2. Now we use the fact that the integral, now I abuse a bit of notation, on C is equal to the integral on C1 plus the integral on C2. And we get that the line integral of the function on the curve C is equal to 7 square root of 42 plus 60, this is 60, minus 25 over 2. An application of line integrals is finding the work done by a system. So in this case, we have that the work is given by the formula, the line integral over the curve C being, for example, this curve in the figure, that usually is the displacement done. And this, as seen in the formula before, is given by the integral from a to b of f evaluated at r times r prime of t. In this case, we don't have the magnitude of r, because simply here we have a slightly different case. It's not a scalar field, what we have, but it's a vector field, but it's just slightly more general than what we saw before. The computation is very similar to what we saw. This was the end of the 4th video on the series of multivariate calculus. In the next one, we are going to talk about theorems, fundamental theorems of calculus, and we are going to see some examples and applications of them. For now, it's all. See you on the next video.